What if I told you that we live in a bubble? A bubble so large that it contains our universe. Our entire universe floating in a sea of other bubbles, each one holding a universe of its own. You might turn to me and say that sounds like science fiction. So here's the part that might unsettle you. Bubble is not my metaphor. It's a word that physicists use in the technical literature. And the idea doesn't come from imagination. It falls out of equations that have already passed real observational tests. Tonight, I want to show you why some of the most careful scientists alive think that the bubbles might be real, and what black holes might have to do with it. And, because we keep things honest here, exactly where the evidence stops and the speculation begins. Let's start with something we've actually photographed. This is the oldest light in existence, the cosmic microwave background, otherwise known as CMB. And it holds a genuine mystery. It's smooth, really smooth. Look at these opposite edges of the sky, regions so far apart that light itself has never had time to travel between them, but their temperature matches to 1 part in 100,000. That shouldn't happen. Two places that have never been in contact with each other shouldn't agree so well. Unless, at the very beginning, they were in contact, squeezed together in a space smaller than an atom, and then torn apart faster than light can cross the gap by an expansion so violent we gave it its own name: inflation. In its first fraction of a second, the universe didn't grow, it detonated, space itself doubling and doubling and doubling dozens of times over in less than a trillionth of a second. In fact, less than a trillionth of a trillionth of a trillionth of a second. Inflation isn't a fringe idea. It solves the smoothness problem. It predicted the pattern of ripples we later found in that picture, and it sits in the standard model of cosmology. But inflation comes with a passenger, something the theory's own architects discovered in the maths and couldn't remove. In most versions of the theory, inflation never stops. It ends in patches. Here, there, regions where the detonation runs out and space calms down and matter condenses, like bubbles of steam forming in boiling water, except in reverse. Bubbles of calm condensing out of a sea that never stops raging. Our Big Bang in this picture wasn't the beginning of everything. It was the moment that our bubble condensed, 13.8 billion years ago. The sea boiled us into being. And beyond our bubble wall right now, the sea is still raging, still condensing new bubbles and new universes. In theory, forever. Now watch the label in the corner, because it matters. Inflation itself is a strong theory, tested against real data. Eternal inflation, the endless sea, is a consequence of that theory. No one has ever observed it. The bubbles come out of mathematics that we can trust. However, that's not the same as seeing one. But you can hold that thought because there is a second road to proving this, and it starts somewhere a little bit darker. In 1974, Stephen Hawking proved that black holes are not eternal. Quantum effects at the horizon will make them glow, and across unimaginable spans of time, they might evaporate completely. And that raises a problem physics has not solved in 50 years. Quantum mechanics insists that information can never be destroyed. But if a black hole swallows a library and then evaporates into featureless radiation, where did all of the books go? This is known as the information paradox and is still wide open in quantum physics. The leading clue is strange. The amount of information a black hole can hold does not scale with its volume. It scales with its surface area, as if everything that falls in is written on the horizon, like data on a two-dimensional page. Some physicists take the idea further. Perhaps all of three-dimensional reality works this way as well. A projection of information stored on a distant boundary. But notice what the horizon has become in this picture. Not a wall, a surface where a universe's worth of information can live, which makes the next question almost inevitable. We can take the mass of everything we can observe, absolutely all of it, and ask how large its event horizon might be, as if it were a black hole. The answer comes close, suspiciously close, to the size of our observable universe itself. And some physicists have asked, was our Big Bang the inside of a black hole forming in another universe? And every black hole in the sky, a door, and our whole sky, the inside of one. If that's true, then we can follow the logic with one more step. Because this is where it stops coming across as strange and becomes something a little bit more like biology. If universes are born inside of black holes, then surely universes reproduce. And in 1972, the physicist Lee Smolin asked the obvious next question. What happens to anything that reproduces, with small variations across generations? It evolves. Suppose each daughter universe inherits its parents' physical constants, such as the strength of gravity or the mass of the electron, with tiny random mutations, like DNA. Universes whose constants are good at making black holes might have more children. Their children have even more children. Generation after generation after generation, the so-called multiverse would fill up with universes tuned to make more black holes. And a universe that's good at making black holes is a universe that's good at making stars. Stars mean carbon. Carbon means chemistry. And if there's chemistry, that means there's us. In this picture, we aren't the point of the universe. We're just a side effect of the universe being good at reproducing. Our observable universe alone contains an estimated 40 billion black holes. If Schmolin is right, you're looking at a family portrait. 40 billion children, and every one of them their own universe. So why on earth do serious physicists actually entertain any of this? Not because it's beautiful or a concept that's in Marvel films, but because of a problem and a little bit of evidence. Let's talk about the problem first. The constants of our universe appear absurdly well tuned for existence. The sharpest example of that is the energy of empty space itself, the cosmological constant. Our best quantum theory predicts a value, and that prediction is wrong by a factor of 10 to the power of 120. It has been called the worst prediction in the history of physics. And if the true value of empty space were even slightly larger than it is, space would fly apart before a single galaxy could form. So why is it so precisely and so improbably small? The multiverse offers an answer, and bear with me on this one. If there are countless bubbles, each with different constants, then most of them are sterile. And every observer who ever asks, why is my universe friendly, finds themselves in one of the rare friendly ones. There's no one in the other universes to ask. If you win the lottery, you don't marvel. Someone had to win it. And here is why this reasoning earned respect instead of eye rolls. In 1987, Steven Weinberg, Nobel Prize winner, used exactly this logic to make a prediction. While nearly everyone assumed the cosmological constant was exactly zero, Weinberg argued if we live in one bubble among many, the constant shouldn't be zero. Just small. Small enough for galaxies and no smaller than it needs to be. 11 years later, astronomers discovered dark energy. The cosmological constant is not zero, it is small. The multiverse framework made a prediction before the data even existed, and the data agreed. That's the universe's receipt. It isn't proof, and other explanations do exist, but it's the whole reason this idea sits in physics departments and not just in films. And we've gone even further than that. We've actually looked. If another bubble ever collided with ours, it would leave a bruise. A disc-shaped scar printed on that baby picture of the sky. Scientists have run dedicated searches through the microwave background hunting for exactly that. And they have found nothing. So far. And you should know the hard critic too, because it's real. Many versions of the multiverse may never be testable, even in principle, and some physicists say that puts it outside of legible science altogether. That argument is alive, and it's still not settled yet. So where does that leave us? It leaves us with this. The bubbles end up falling out of equations that we trust. The reasoning has one genuine prediction to its name. The hunt for the scar across our universe came back empty, and still continues to this day. So, what if I told you that we live in a bubble? I couldn't prove it to you. No one on Earth can. Our universe is all we've ever measured, and it means a lot saying it out loud. But somewhere between a smoothness in the oldest light or a paradox at the heart of every black hole, the bubble did stop being fiction. It became a question that physicists ask. And any black hole that you might see in the night sky might just be a door to another multiverse.